Greg, W1JXR, talking about Nano VNA. So why don't you go ahead and take it, and you've got permissions to share, Greg.
Okay, very good. Thank you, Jim, and say good evening to everyone from the club. Thanks for having me tonight, and hopefully people will take something away from the presentation. Let me go to share screen here. Okay, are you all seeing the screen?
Yes.
All right, very good.
Very good.
So we're going to talk about the Nano VNA, and what we're going to talk about is first of all, what is a network? It's called a Vector Network Analyzer. So we'll talk about what is a network, one-port and two-port types. We're going to talk about how can we measure RF networks and a little bit about something called S parameters. We'll talk about what is a vector network analyzer, how does a vector network analyzer work, why do you need to calibrate the network analyzer, the short open load through calibration kit, how to use the Nano VNA. We'll go through a little bit on the menus and the display. We'll talk about some free PC software that you can download to use with the Nano VNA. And we'll do a demonstration of a typical measurement. And we'll talk about there's a demo board that you can get. We'll talk about that. So, what is a network? Well, a network is any black box, any electrical black box, and you can have a one-port network. Some typical one-port network devices might be your amateur antenna. That's a one-port network. An RF load, an RF transmission line, open or shorted stub that might be part of a antenna system. There's a variety of things that are one-port networks. How about two-port networks? An RF amplifier, that would be a two-port network. It has an input and an output. An actual piece of coax, a RF transmission line, is considered a two-port network.
Hey, Greg.
Yes.
We got a comment in the chat that your audio is a little low.
Okay. How's that? Is that any better?
Yeah, perfect.
Right.
Okay.
Thanks.
Sorry about that. So two-port networks, RF amplifier, transmission line, an RF filter. Those are all examples of two-port networks. If you had like phasing stubs on a vertical phased array system, that would be a two-port network. So let's talk about measuring RF networks. At low frequencies, when we're dealing with circuits that are, at audio frequencies or even IF frequencies, we can go in there with equipment and actually measure input and output voltage and current, and those things are characterized by either Z parameters, Y parameters, or H parameters, but we can go in there and we can measure currents and voltages and stuff. But when you're dealing with RF circuits, especially when you get into the much higher frequencies, we can't go in there and measure voltage and currents. It's just not practical. And as soon as even the parasitic capacitance of a probe or something often alters the operation of the RF circuit. So they tried to come up with a way of looking at RF circuits by just monitoring the input and output ports. And that's essentially what a vector network analyzer does. And we can think of that RF network similar to the optical analogy you see here with a lens. If you have some sort of a lens and you apply an incident light beam to the lens, well, a certain amount of energy is transferred through the lens and is transmitted out the output side of the lens, and then a certain amount of that incident light energy is reflected back off the surface of the lens, and you see those things indicated in the picture. Well, the same thing happens with an RF port or a RF network. You can apply a certain amount of energy to the port. Some energy might be reflected from the port, and then energy might travel through the network and out the output port. And when we look at these things in an RF circuit, you can see that we can learn a lot about the circuit. All of the reflected things on the left, we can learn about SWR and reflection coefficient, even what the impedance is, looking into that port, and something called return loss. And of course, by looking at the energy that's transmitted through the network, we can look at things like gain or loss, transmission coefficient, insertion phase, and group delay, and a bunch of other measurements that can be done on the network. And I'm not going to spend a lot of time on this chart, but they've characterized this looking at the ports and looking at the energy that flows from the input to the output port and the energy that flows from a port and is reflected back. They refer to those things as scattering parameters, or S parameters for short. And there's a lot of math here and so forth, but basically the takeaway here is you apply power to a port, and you can look at the reflected power from that port, or you can look at the power that goes through the device and comes out the output port. So how does the network analyzer work? So we have our network analyzer here shown in the block, and the thing at the bottom, that's our device under test. That's our network that we're trying to test. And the way the network analyzer works is you have an RF source. It puts out a signal at a certain frequency, and they split that signal. So you have two identical signals coming out of this splitter here. I don't know if you guys can see my cursor, but the splitter here, you have two identical signals coming out. One of the signals they send right over to an RF receiver, and they call that R the reference reading. The other signal, identical to that first one, they send out. You can change the level of it, and they send it out, and send that out port 1 of the analyzer, which is connected to one of the ports on the device under test. Any energy that's reflected back from that input port on the device under test is reflected back, and this directional coupler senses that reflected signal, and that reflected signal is sent over to receiver A. The signal then that is, goes to the device under test and travels through the device under test, comes out the output port. That goes to port 2 of the network analyzer, and that signal is routed over to receiver B. And by looking at the levels of these three receivers, A, B, and R, and taking ratios of A to R or B to R, we can calculate all the things we need to know about this RF network. So let's look particularly now at the Nano VNA itself. It's a little unit. They have some bigger ones now. This one I think is the first ones that came out were a 2.4-inch screen. I think they have a 4-inch screen out now. I only have the smaller one. It is a bit hard to use the screen. It is a touch screen, but you need to really use a stylus or something because it's very the screen is so small. They give you a little thing on a string. It's kind of like a guitar pick.
It is a guitar pick.
Yeah, and you can use that as well to touch the screen. You see, it has two ports. Transmit out, that's where the signal comes out of, and then the RX in port is if you're sending your signal through an RF network, and it's a two-port network, then the output port of the network would be connected to RX in. It has a USB connector which you can connect back to your PC, and that's also used to supply power to the unit and charge the self-contained battery. It has an on-off switch, has a couple LEDs, one that says tells you what the battery status is, and the other one that tells you that the thing is turned on. And then it has a multifunction rocker switch, which you can rock from side to side, like to move a cursor from the beginning to the end of the screen, or you can push it as a button, and then the different menus come up on the screen. One of the things that I did with mine, and I like to do with Network Analyzer, just a little bit of history with myself. Network analyzers. I'm retired senior principal engineer from Raytheon Company, and I retired at the end of 2019 after spending 42 years with them. And my first network analyzer that I worked on was back in the mid 70s, and it took two 19-inch wide, 6-foot-high racks of equipment to do what this little handheld palm thing does. So we've certainly come a long way. That's for sure. But one thing I recommend, especially the SMAs are nice connectors, but they will wear. And if you're going to be doing a lot of connecting and disconnecting with those SMAs, I highly recommend picking up a couple SMA male to female adapters like shown in the picture here, and just screw them on your SMA ports, and then you can connect and disconnect your cables to the output side of those adapters. And if the connectors wear or become damaged or whatever, you haven't damaged the ports on your instrument. You can take the connector saver off, throw it away, and put a new one on. So I highly recommend that because those connectors on the device are actually soldered right down to the printed circuit board. So if you damaged the actual connector, it would be a bit of a pain in the neck to have to replace that. Oh, let's talk a little bit about the specs. What are the specs? They have some units now that go a little bit higher, but frequency range is 500 kilohertz to 900 megahertz. It goes 500 kilohertz to 300 megahertz directly, and then it uses harmonics from the source to get up to 600 and 900 megs. The RF output is minus 13 dBm, so that's 1/10 of a milliwatt. So you can see that we're dealing with very small signals here, but it's a very sensitive device. You don't need a lot of power. And then the nice thing about that is, if you're testing an antenna or something, you're not going to bother anybody because you're putting out such low power. Dynamic range, 70 dB on the lower frequencies, and then it falls off 60 and 50 dB as you go up higher in frequency. But dynamic range is just how much of a difference in signal level can it see from the maximum signal to the noise floor. Display, like I said, is a 2.8 inch. They now have a 4-inch one, I believe. It's got a USB interface for data interface and also for power and charging. It has a built-in LiPo battery. The number of points, and this has to do with the processor in it, the number of points as you sweep from your start frequency to your stop frequency is 101 points. And so that's probably the biggest disadvantage of this unit. So if you're sweeping over a very wide frequency range, you only have 101 points. That's a pretty big jump, between steps. But they solved that with the free software that they have. You can do multiple segments of 101s, and in the software they stitch all those segments together, so you can get more resolution if you use the free software. The display, you can have 4 traces and 4 markers. There's 5 memories for calibrating and storing setup. And the frequency error, it's pretty good, frequency-wise. It's 0.5 parts per million frequency error. So at 100 megahertz, that would be an error of only 50 hertz. So that's not bad. All right, so let's look at the what's inside the Nano VNA. This is a block diagram of it, and I've added some annotations. Starting up at the top left, you see the RF bridge. That's the device which separates the forward and reflected power. To the right of that, there are 3 RF mixers that go into 3 ports of the analog to digital converter. That's the TLV 320. The digital to analog converter through an I2S interface over to the microprocessor CPU. That's the STM32 there, and of course that has all the switches and the USB ports connected to it, and it also drives the liquid crystal touchscreen or display. Providing the RF signal, there's a synthesizer chip, which is VCXO based. And that little synthesizer supplies the RF signal to the instrument. So that's basically, at a high level, block diagram, what's inside the Nano VNA. So now let's talk a little bit about how it works. So first we're going to look at how it does a reflection measurement. That would be S parameter S11. Or for us ham radio guys, the reflection measurement would be, that's how we measure SWR. So what happens, well, if you guys can, I got a train going by my house next to a track here. If you hear a train in the background. But the synthesizer applies an RF signal to the RF bridge. The microprocessor would command the synthesizer for a specific frequency, and then the synthesizer would put out that frequency, and that energy would be sent to the RF bridge. The synthesizer also puts out another frequency called the local oscillator, and that frequency is sent to the three mixers, the bottom port of the three mixers, as the LO for each of the mixers. The RF signal that's sent to the bridge is also sent to the middle mixer, and that middle mixer downconverts that signal from an RF to a lower frequency, probably in the kilohertz range, and that signal goes into the digital to analog converter and is converted from analog to digital ones and zeros. But that gives you the reference of what you're applying to the bridge, and that will also be applied to the device under test. So the bridge takes that signal and forwards it to the device under test. Here, because we're doing a reflection measurement, we're probably talking about a one-port device, so you wouldn't have anything connected to the RX port. So that might be our antenna that we're trying to measure. The bridge then, the energy would be, any energy because of a mismatch would be reflected from the device under test back to the bridge. The bridge separates that forward energy from the reflected energy, and it sends that reflected energy to mixer number 1, and that mixer downconverts that energy as well, and the representation of the reflected signal is sent to the A to D. The A to D would then take that information, send those two signals in digital format over to the microprocessor, and then the microprocessor would do the math to take the reference signal and the reflected signal, and through math equations it can figure out what the SWR is, it can figure out what the impedance is. If we were now measuring what's called a transmission measurement, or S21, for example, if this was a piece of coax and we wanted to measure the insertion loss of the coax, once again the synthesizer sends out a signal to the bridge. The synthesizer also sends out the local oscillator signal, which is offset from the main signal by some number of kilohertz. That main signal is also sent to mixer number 2, so we get the reference signal again in input port 2 going to the digital to analog converter chip. That signal is sent over to our device under test. The signal flows through our device under test. The output of the device under test goes into the RX port, into mixer number 1, and then along with the local oscillator signal is downconverted to input number 2, or what's considered the through signal, and that goes to the digital to analog converter. And by taking and doing mathematical operations on the through signal compared to the reference signal, you can calculate gain or loss. You can calculate phase relationships. So one thing that's happening here is these signals, as they're digitized in the A to D and sent over to the microprocessor, they do that in a complex math or vector math format. And so not only is the amplitude of the signal or conveyed to the microprocessor, but also the phase of the signal is conveyed to the microprocessor, so they can do complex mathematical operations of vector quantity. So not only can they measure the amplitude and strength of the signal, but they can measure the phase relationship between the various signals. So this is what the Nano VNA board inside the little box actually looks like. Upper left-hand corner, there's your charger circuit. Just below where it says charger, that big chip there, that's the CPU. To the right of that, at the upper right corner of the battery, that's the analog to digital converter chip. In the middle of the, just above the analog to digital converter chip, is the phase lock loop synthesizer chip. You see the battery there, of course, and then over toward the right, you see the 3 chips, one above each other. Those are the 3 mixers, and then leading out to the 2 SMA ports, and you see, as I mentioned, those connectors are soldered right to the printed circuit board. Up at the top, you see the little rocker push-button combination switch there. You see the on-off switch, and you see the USB connector at the very top. So let's talk about calibration. So because we're doing precise vector measurements here, where we're concerned about not just the magnitude of the signal, but we're concerned about the phase of the signal, calibration of the instrument is very important. And the way that anytime we try to do a measurement with an instrument, we always introduce errors. No matter what we do, there's errors. So there's no way that we can take a measurement and have it be a perfectly accurate measurement. There's always going to be some errors associated with the measurement hardware and so forth. So how do we compensate for those errors in the hardware so that we can get extremely accurate measurements? Well, the way that we do that is we use what's called a calibration kit. And there are 3 little SMA male connectors that come with the Nano VNA, and they've manufactured those 3 little connectors so that one of them is a perfect RF short circuit, one of them is a perfect RF open circuit, and the other one is a perfect RF 50 ohm load. And so there's a menu that you can bring up to do calibration after you've set the analyzer up for your frequency range. You set a start and a stop frequency, and after you set up that frequency range, you press calibration, and the first thing it tells you is, apply the short. So you screw on the short, you hit the thing, it goes off and takes a bunch of measurements, and then it comes back and says, okay, put on the open. You take the short off, you put the open on, you hit the open thing, it goes off and takes a bunch of measurements, and then it says put on the load. You take the open off, you put the load on, you hit the button, it goes off and does a bunch of measurements. It then you leave the load on, and it asks if you want to do I'm forgetting the word. Hold on. It's where you measure crosstalk as, what is it, isolation. I'm trying to find it here. Of course, I can't find it when I want to, but anyways, it asks you to do that. And you do that by leaving the load on. It measures the isolation between port 1 and port 2. And then you take that off, and it tells you to put the through on. So in addition, what comes with the network analyzer is two little SMA to SMA coax cables. You take one of those cables and you put it from port 1 to port 2, or the RX port to the TX port, and then you press the through button. It goes and does a bunch of measurements, and now it says calibration is done. You can store that calibration in one of the memories, and you press a button that's called correction, which means it's going to use those error vectors that it calculated during that short open load sequence. It's going to use them in all the measurements that it does. So one way to look at this is if you look at that little diagram toward the bottom of the slide there, you see I've got a vector that I'm trying to measure, S11M, and that's the measured value of that we measured for some particular measurement that we're trying to take. But the actual measurement of that device that we're measuring is that S11A over on the left. Well, what it does inside the mathematics of the instrument, it takes that S11 measurement and it applies 3 or 4 error values that it calculated when we put the short open load on, and it can actually back that measurement up and take out the errors in the S11 actual measured vector and figure out what that S11 actual with the errors taken away, and it corrects for all those errors. And this is done very accurately because all those error vectors not only include amplitude errors but also include phase errors. So it's mathematically, vectorially taking out all of those errors, and you can get very accurate measurements down to, you know, 1/10 of a dB in amplitude and probably 1 degree or so in phase, which is pretty good. So the terms, the error vectors that it's taking out are there's 6 terms for each direction. You've got directivity error. The bridge within the instrument is not perfect. There is some leakage within that directional bridge, and so it measures that directivity error and takes that out. There's crosstalk between the input and output ports, where you might get some you might get some leakage in the receivers A and B inside the unit. It measures that crosstalk and it takes that error out. The input and the 2 ports on the network analyzers are not perfect 1-to-1 50 ohm exactly ports. There is a slight amount, I mean, they're very good connectors, but there's a slight amount of SWR on the ports of the instrument itself. So when you apply an ideal short open load onto those connectors, it actually can calculate what the loss is due to the VSWR of the connectors on the instrument itself. That's called source match and load match, and it can take those errors out of the measurement itself. And then, of course, as you're sweeping in frequency, going from a start frequency to a stop frequency, there'll be some frequency error as you go from frequency to frequency in the detected levels. And whether you're doing a reflection measurement or a transmission measurement, and that's called frequency response error. So it's these 6 error terms, or 12 terms total if you're using a 2-port device, that the unit calculates and uses from the calibration that you do when you put the short open load on to the unit. Okay, so now let's talk a little bit about, oh, by the way, if there's questions at any time, please don't hesitate to interrupt or ask. Do we have any questions up to this point? Okay. So now let's talk a little bit about the displays and some of the menus and so forth. Well, one thing I must say is that when you buy the Nano VNA...
Excuse me, Greg?
Yeah.
Excuse me? I was on mute. You were asking if anyone had questions. I'm wondering if you would make your presentation available to the club.
Sure.
Okay. Ralph can probably put it on the club server.
Yeah.
Thank you.
No problem.
I think you have my email address, Greg. Sure.
Yep.
Thanks.
So if when you get the Nano VNA, like many of these things, I mean the price is very attractive, but because of that price, don't look for much in the way of documentation. In fact, the only documentation that comes with the unit is an 8.511 sheet of paper with this information on it. So if you've never used a network analyzer before, good luck. That mainly was the incentive to putting this little presentation together, because I've been using network analyzers for a very number of years. So when I saw this menu, this is all familiar stuff to me. But for the average ham who's never used a network analyzer before, I'm sure this would be just, well, what is this? All this stuff, how do I use it? So that's what I'm hoping to help you with here. So there's a home menu on the Nano VNA. When you press that little rotary button thing, you press it down, the home menu comes up, and if you click on the display, the top item on that menu, then the next menu comes up with trace, format, scale, so forth. Trace allows you to select up to 4 traces that you can have on the screen, and they are color-coded on the screen, as you see the colors here. Format, when you select that, it allows you to choose what's the format of the XY coordinates on the screen. The left to right, or the X coordinate on the screen, is always frequency, but the vertical axis of the screen, you can change that, and you can have it log magnitude in dB. You can read phase. You can do delay. It'll actually show a Smith chart if you know how to use them, or SWR. You can hit more, and then there's more. You can get a polar, a linear. You can look at the real or the imaginary component of the impedance, or you can look at the actual resistance or the reactance. For most ham radio operators, for what you're going to use that for, 9.9 times out of 10, you're probably just going to want to just hit that SWR button. The only other one that might be useful would be the log mag button, but more than likely, most of the time, you're just going to want to hit that SWR button because you're looking at an antenna or something, and that's what you want to do. Scale, that just allows you to, all of these things default to pretty reasonable numbers, but if you do want to go in there and change it, on the scale, you can change the scale per division of the little divisions on the screen, or wherever the reference position is, you can move that up or down. But 9.9 times out of 10, the default will work fine. The next one you're going to want to select is channel, and what that means is, are you doing a 1-port measurement, or you want to just look at channel 0 reflection, or are you doing a 2-port measurement, which means you want to click on channel 1 through. So if you're measuring an antenna and you're just doing a reflection measurement, you want to make sure you've clicked on channel 0 reflect. Transform I won't get into. That's more technical stuff if you're doing special operations with stuff that you're seeing on the screen. There's built-in firmware that does some special processing for certain types of measurements, but for stuff that the average ham is doing, there's nothing there that you really need to worry about. Okay, the next thing down on the home menu would be the markers, and so when you hit marker, the marker menu comes up, and you can put up to 4 markers on a trace. You can take that marker and just select it, and then I think it just goes to the beginning of the trace, and then you can move it around. Or you can take that marker and immediately put it to the start of the sweep, the end of the sweep, or the stop, the center, or the span.
Greg, on the marks, do they show like a horizontal line on the display as well?
They show a little triangle, and then you can move it along the display so you can see where the marker is.
And does the marker indicate both the horizontal and the vertical value at that point?
Yeah, there's a little readout on the screen for each of the markers, and so you can get the both the frequency value and whatever the vertical scale is, whether it's SWR or return loss or whatever.
Thank you.
You're welcome. Okay, the next one is the stimulus menu. And when you're first starting up the network analyzer and you want to set it up, one of the first things you'll do is you'll go over to the stimulus menu, and you want to set the network analyzer up for whatever your situation is. So you have to tell the network analyzer sweeps from a start frequency to a stop frequency. And so you have to tell it what the start and the stop frequencies are. So for example, if you're testing a 2-meter antenna, you might want to sweep over the 2-meter band, 144 to 148. So you would hit start and you'd punch in 144 megahertz, and you'd click stop and you'd punch in 148 megahertz. I find the start and the stop the easiest way to do it, but another way that you can do that frequency sweep is you can specify the center of the screen, and then you can specify the span, which is what the width of the screen is. But I find it more intuitive just to do the start and the stop. You can also measure at one single frequency, and so you can have the thing actually work as like a little source, and so it'll actually put out a CW frequency at one frequency rather than sweep. And if you do that, then you would hit the CW freak button and just enter the single frequency that you want. Okay, so after you set up the analyzer with your start, stop, and so forth, the next thing you have to do is calibrate. So you'd go over and you'd hit the cal button in the main menu. That would bring you over to the calibrate menu. You would tap on calibrate, and that's where that menu would come up that I talked about earlier when we were talking about calibration, that says open, short, load, isolation, and through. So that's where it's going to walk you through, okay, put the open on, hit the button, put the short on, hit the button, put the load on, hit the button, leave the load on, hit isolation, take the load off, connect the cable from one connector to the other connector, the through connection, hit through, and then you hit done. And then when you hit done, it sends you back. And so The next thing you should probably do there is you want to save this calibration. So you would just hit save, and then you could select save 0 through save 4 and just save this calibration in one of the memories. So you can have multiple calibrations for different frequency ranges already set up within the analyzer. And if you make a little note of what they are, you can recall any of these 5 saved positions, and those calibration values will be pulled back into the analyzer ready for you to do a measurement. You can reset the cal at some point if you want to do that. And then after you save that calibration, you want to make sure that that button that says correction is lit. If it's not lit, then you want to press it, and once you press it, it should sort of like light up, which means that, okay, I have the calibration constants, and I'm going to use those to correct the measurements. So you want the correction function to be turned on, so to speak.
Greg, this is Peter.
Yeah.
Would you do calibrations for various ham bands?
You could. Yeah, you could do them for various ham bands, or I typically do it for, things that I'm measuring. But yeah, you could do it for, ham bands, but it's device dependent. So you got to think about, okay, what it is that I'm measuring and what frequency range do I want to look over. So you want to make sure you have a calibration that covers that range. Did that help?
It did. Thank you.
Okay. And obviously, for example, if you've calibrated from 100 to 500 megahertz, but you're measuring a device that's centered around 146 megahertz, well, you probably want to pick a smaller start-stop window because you remember those 101 points. Those 101 points that you're doing the measurement are over that start-stop interval, and so you're going to get a lot less resolution if you're over a very wide range. So you might want to do a calibration over that narrower range when you're measuring a particular device. And recall is just a way that you can go in, and if you have things saved in those 5 memories, you can recall them. Config, there's a bunch of like a touch cal and touch tests. If for some reason you're having a problem with the screen, there's a way to touch test. There's a way to test the screen. Touch cal, I think, is a way of recalibrating the screen if somehow it got fouled up. Version is just tells you what version of the firmware it's running. DFU, I think, is a way of either downloading or resetting the firmware. I've never used that, actually, so I don't know what that does. And then, of course, close just closes the home menu. So that's the whole menu structure. It's a little bit intimidating, but you don't end up using all that stuff when you're doing typical measurements. There's a few things that you use every time, and it's not all that difficult. But because of the lack of any documentation that comes with the network analyzer, one of the things I suggest is if you have a Nano VNA and you want to learn more about it and then actually get the free software that you can download, go on the web and join this Groups IO Nano VNA users group, and there's a horde of documentation and information, and user manuals and stuff on there that you can download, and you know, there's a bulletin board chat kind of thing. So if you have questions, you can go in there and post a question. And there's a lot of brilliant people on there who know a lot about the Nano VNA and have used it quite a lot. So I can't imagine any question that you wouldn't be able to get some sort of an answer to. But it's a great asset. Okay, so one of the things you can also do is go on to the Groups IO site, and they have a download section, and you can download a program called Nano VNA Saver, and it's a free to download program. You can download it. I'll do a little demo of it here shortly, and it works quite well, and you can completely control the Nano VNA from the software, and so you can use your PC or a tablet or whatever, and if you want a bigger screen to look at and a little easier to use, rather than clicking the little things on the touch screen, you can use the Saver software. The other thing it does here is you see this where it says segments, and you do a sweep. So if you're doing a measurement from some start to stop frequency and you have your segments set at 1, it's going to take that 101 points and it's going to distribute it between your start and your stop. But if you set that segments to 10, it's then going to break that start-stop frequency up into 10 segments, and it's going to apply those 101 points to each of the 10 segments. So now you've got 1,000 points between your start and stop.
So this is communicating live to the Nano VNA through the USB interface?
Yes, it is.
Awesome.
Yep. And so it takes a little longer. You'll actually see it fill in the graph as you tell it to sweep for these various segments as it's talking to the Nano VNA. But you'll obviously get a lot more resolution in your data plots. Okay, so let's measure an antenna with the Nano VNA. Remember, the antenna is a 1-port device. So the first thing we want to do is we want to set the start and stop frequency to cover the frequency range of the antenna that we're trying to measure. The next thing you would do is you would go in and you would calibrate the Vector Network Analyzer with the short open load, and I should have said through there too. You would go through the whole calibration sequence, and it would measure all of the error terms over that start and stop frequency that you selected, and you could store those away. The next thing you would do is you would select display and then channel, and make sure that you've selected channel 0 reflect as the type of measurement that you want to do. You're doing a 1-port reflection measurement when you measure an antenna, so you want to make sure the analyzer is set up in that fashion. So you would connect the antenna to the TX port on the VNA. Set the display trace to trace 0 if you wanted just a single trace, which in this case we're interested in looking at the antenna SWR, so you would just set up a single trace. Set the trace format to SWR via the menu. And then you could then read the actual SWR of the antenna over the start to stop frequency band that you set up. Okay, so I'm going to stop sharing the presentation here, and I don't know if you guys can see, But I have my Nano VNA here, and for ease purposes, I took the Diamond handy talkie duo band 2 meter 440 handy talkie antenna off of my handy talkie, and I screwed that onto the TX port of the Nano VNA. So we're going to measure my handy talkie duo band antenna. I've set the Nano VNA up. I already calibrated it. I'm not going to bore you guys with watching me put short open loads and throughs on. So I already calibrated, and I calibrated it for a start frequency of 100 megahertz and a stop frequency of 500 megahertz, because this is a 2 meter 440 antenna, so we want coverage in the 2 meter 150 meg range, and we want coverage to measure the antenna in the 450 megahertz range. So I set 100 to 500 megs as the start stop. Okay, so I'm going to go and try to share screen again and see if I can pull up the Nano VNA saver. Okay, are you guys seeing my Nano VNA saver screen?
Yes.
Yep.
Okay, so I've set the thing up. You see it's 100 megahertz to 500 megahertz. I've set up 10 segments. When you first bring this up, you have to hit this button down at the bottom here that says connect. It'll go out through the USB port and find the Nano VNA and connect to it. And then once it's connected, then you're talking. So all you do is once you've got all this set up, you can set up your screens. I've set up here for a signal screen. I think you can have up to four displays on the screen at the same time. But since we're doing a single measurement here, I set up one big screen here, and I set it up for, you see down at the bottom here, you see the frequency axis starts at 100 and goes out to 500 on the far right. And I set this up for SWR, and SWR of 1 to 1 is at the very bottom, and SWR of 7 to 1 is at the very top. I set that range up to kind of blow up, but you can go up to 25 to 1 SWR or whatever you want, but typically we're interested in looking at the lower stuff, right? All right, so once you get that set up, you just go and you hit this button here, sweep, and I don't know if you can see it live, but it's actually filling in the plot there, and you can see it changing a little bit from the plot that I had before. Okay, so SWR, you see we've got a nice dip here. If I take, here's the little triangle cursor, Bruce, that we were talking about. You can take that cursor, and if I click on the dip here, it brings that cursor down, and you can see that minimum SWR right now is showing up at 155 megahertz. Now, one thing I must say is, because I'm connected to the analyzer, and this antenna, really wants a ground plane connected to it. I can take my hand, and you guys can't see it live because, but if I look at the screen of the analyzer, when I put my hand near this thing, that trace is bouncing all around. So I'm not really getting a real accurate measurement of the antenna here because I don't really have a good ground plane. I suppose if I tried to simulate a ground plane, I would get a better reading here. But because this type of antenna is wants a ground plane to work correctly, some of these frequencies are a little off. But you see the dip here at the 2 meter band in this range, And then way over on the right, you see the other dip here at the 443 megahertz. That's the 70 centimeter dip. There's also another dip here about in the 255 megahertz range, but the main ones that the antenna wants, of course, are the 2 meter and the 440. So you can go in and, like, for example, if I want to, you can hit display setup. If I want to change from SWR, let's say I wanted to measure return loss in dB, I can hit that. And now I'm measuring return loss. Let me sweep that. And so now you're measuring internal. It's hard to see the dip here. You see the dots are so far apart because the resolution. I mean, really to get a better measurement of the antenna, the way to do it would be to take one measurement over the 2 meter band and then take another measurement over the 70 centimeter band, and you'd get more accurate measurement, better resolution.
So, Greg, it looks like it's updating as it goes across the horizontal scale 3 or 4 times. Is that the software doing the separate tests and then merging them all into one graph?
Yeah, exactly. I've set it up for 10 sweeps, so it's going to take 10 sweeps, 101 points in each sweep, and then it merges it all together in one graph.
And each point is each point that you see when you can see the individual dots on the screen.
Yep. Yeah, that's each frequency point in the sweep. Yep.
The data associated with the sweep, the data associated with the marker, it is up here where it says marker 1 or whatever.
Yep. Yeah, there's all kinds of data. It's not only does it give you, frequency and VSWR return loss. It actually shows you what the complex impedance is at that point, what the series L, series C, parallel R, parallel X. So there's quite a bit of information. Like I say, because all of these calculations are done with vector math, so there's not only magnitude but phase. It's a very complex sequence of mathematical computations that's going on inside this little box.
Could you put another marker up in addition to marker 1, Greg?
I believe so. Let me see. I'm trying to remember how to do that. I actually haven't used this software a lot. Let's see. It's somewhere here. I'm sorry, I'm drawing a blank as to where that is.
Could it be as easy as clicking the right mouse button on the display and it'll say add marker?
Could be. Let me see. Frequency axis. Nope. That changes display settings. I know I've done it before.
Oh, well.
But theoretically, you could do that, correct, Greg?
Oh, yeah. You can have up to, I believe, 4 markers on a trace, yes.
Try display setup in the lower left corner.
That's where I was before. I'm just trying to, I think it's on here somewhere, but I'm trying to.
So right click on the left side, because you may get something different if you right click.
Right, that's what I was thinking. right-click in the marker.
Left corner, yeah. Now go.
Oh, markers, add, here you go. Right here, down at the bottom, it says markers, add. So I've
go.
now
That
added,
did it. You did it.
added another marker.
Mhm.
Not sure where I added it.
There's a radio button, a radio button next to the green marker 2 on the
Yeah.
left.
Click on that right there.
There you go. Yeah.
There you go.
So now I've got the green marker and the red marker. Looks like one of them. Yeah. So I think you can do up. I think you
Where
can do
was
up to
the
4 of
head
those.
markers? Where was the button that lets you add a marker?
You go to display setup,
Yes, sir.
and then at the very bottom where it says markers, you can
So-
add. You can add in.
Yeah, the
remove.
So that
the pop-up is not showing up on the stream.
Right.
Oh yeah. Oh, I'm sorry. Yeah.
Okay.
Yeah. If you hit display setup, and then another menu comes up, and at the very bottom of that, you can add or remove markers. I knew it was on there somewhere. I'd done it before, but
Greg, there's up here under marker 1, marker 2, there's a choice of enable data marker. What will that do?
it says no. That's enable delta marker.
Oh, delta. Okay.
So what it'll do is if you have 2 markers, it'll give you a readout the difference between the 2 markers. That's very handy. Like if you're measuring a bandpass filter, you would place the one of the markers on the rising side of the bandpass filter, 3 dB down from the top, and you would place the other marker on the falling side of the bandpass filter, 3 dB down from the top, and then you would do delta marker, and it would give you the 3 dB down bandwidth of the filter.
Mhm.
Or you could measure the 60 dB down point or whatever you wanted. So if you wanted to see what the skirts of the filter look like, you could do that.
Sure is powerful.
Yeah, it's an amazing little device for $50. Let me go back to the presentation.
Greg, you see this device in my hand?
Hold on, let me close my screen. Yes,
Are you familiar with this guy?
I have one.
You have one.
Yeah, yeah.
Here's
that's
the
a-
manual.
that's an early predecessor to this. I also have another one, which I don't know if you can see my screen, but another one here. This is a vector network analyzer that was designed by DG8 SAQ, a ham over in Germany. He had written a bunch of QEX articles, and then a company called SDR Kits over in Great Britain manufactured these for him, and I bought one. Probably 8 years or so ago, but that was close to $500. So
Yeah, that's right. I bought mine from HRO 5 years ago, and it was close to $500. But here, can you see this? This is the software manual that goes with this thing. And
Yep.
as you've been talking about your software, I've been following the manual. It's
Yeah.
the manual. It's the same software.
yeah, very similar software. All the network analyzers use very similar software. So
But since you and I both seem to have this mini VNA, you find there's a lot of things that the Nano will do that the mini will not, or are they
no, it's It's basically the same thing. I mean, the nice advantage of the Nano VNA is it's self-contained, it's built-in batteries. That the only way you can operate it is to, hook a USB cable up to it and hook it up to a PC or a tablet or something, right? So
This one works with Bluetooth through my Android.
Yeah, that's right, Bluetooth. But you need another device, right? That's what I'm saying. Where
either a tablet or an Android phone. And
right.
I use Android phone, so it works great for me.
Yeah. But it's hard to beat the Nano VNA for $50.
I know. I'm going to go to HRO and ask for my $450 back.
Yeah, no kidding.
Good luck. Hey, Greg.
Yeah.
If you're only doing a reflection measurement, do you need to go through all the calibration steps or just short open load?
Yeah, actually, you only need short open load. The isolation and the through measurement is only needed really if you're doing a two-port network. But you know what? When I do a cal, since I'm doing the cal, I just do the whole thing.
Yeah. Okay, thanks.
I have a question.
Yeah.
It seems there are many different versions of the Nano VNA or different hardware iterations of it for sale here. Is there one that were reputable, reliable?
Yeah. So I would recommend R&L Electronics. They're a ham or distributor. They have both the Nano VNA and the Tiny SA, and both of the versions that they have are very good ones. So I would recommend them as a source.
Mm-hmm. Another question.
Yeah.
I understand the purpose and value of the port saver that you recommended here. If you were also interested in maybe saving yourself a lot of twisting of SMA connectors on and off, you could use an SMA to BNC type connector here.
Yeah.
Is the insertion loss likely to be about the same there? Have you been down this road already?
Well, I mean, so the problem is they only give you a cal kit in SMA.
So you'd have to get your own cal.
Right.
Oh, but
right. If you had a BNC cal kit, then you could put the adapter on, and then you could calibrate in BNC. Right.
Mm-hmm. Yeah.
But
or you'd have to put two adapters on and go back to SMA. And then you'd have
right. Well, you just leave the SMA connector saver on, and then just put your SMA to BNC adapter on the top of that. I mean, that's the whole purpose of that connector saver is you're not mucking with the ports on the instrument itself.
Yeah.
But I mean, so you're doing a calibration at the reference plane of the SMA connector. So as soon as you put a BNC, I mean, I've got SMA to SO239 adapters because when I want to measure an antenna with a PL259 on it, right?
Yeah.
And so you are introducing some error, some loss that you're not calibrating for, but because the connectors are so small, for most measurements that us hams are doing, it's not going to matter, right?
Yeah.
I mean, when I was at work and we were measuring sensitive, microwave components, we couldn't do that. We had to measure in whatever reference plane the connector type for the device under test was. So we had multiple cal kits of all different connector types and waveguides and all kinds of stuff.
Mm-hmm.
Okay.
Greg,
yeah.
I've got one here. It's called the S-A-A version 2. And that one goes up to 3 gigahertz and 201 points versus 101.
Yeah.
And if you use the EOSB, it has 1024 points per segment.
No, good. It's
a bit of an upgrade.
Is that a variant of the Nano VNA line?
Yeah.
Okay, yeah, I'm not familiar with that.
The menu
Yeah,
system's the same. It's just a
Yep.
little bit better range, bigger
Yeah.
battery.
Yeah, yeah, yeah. It sounds like they put a little more heftier processor in it and so forth. So I'm sure there'll be upgrades as they go along. What was the cost of that?
This one was like $60.
Oh, that's not bad. Yeah.
Oh.
Did you get it on eBay or where'd you get it?
You know, I can't remember.
Okay.
Because I got this like 2 months ago.
Yeah. Hey, Jim, can you stop sharing? I just want to. There's a couple more slides I just wanted to show.
Okay.
Let me see if I can go back here. Okay, let's see if it'll let me continue on here. I think I have to hold on. Too many screens here. Let me see if I can get this going again here. Hold on.
You're doing fine, Greg. I have a question regarding the calibration.
Yeah.
Do you calibrate before each device that you're going to measure?
I usually do, although this calibration, this measurement that I just showed you, I calibrated the network analyzer, I don't know, three or 4 days ago. So I didn't recalibrate, but it depends. I mean, if you've calibrated and it hasn't been an extremely long time, and the calibration frequency range that you have will work for the thing that you're trying to measure now, then there's no reason why you couldn't use it. So there's two things that happen. So you want to optimize your calibration for the thing that you're trying to measure, so you get the most resolution within your measurement. So that might be a reason why you might want to recalibrate for some particular device. The other thing is so you did a calibration, let's say a week ago. Well, there is some amount of drift associated with this instrument over a period of time, and so. At some point, a calibration that you did, some number of days ago might not be as totally accurate as one that you do fresh. So there is a certain amount of drift associated with these instruments, and at some point, you might want to recalibrate just to make sure that you're getting the most accuracy you can. There is some drift associated with these. Will the old calibration work? Sure, it probably will work, but there might be a little bit of error with it. For most measurements, it probably doesn't matter. But I always, if it's been a little while, I take the time and I do a fresh cal.
Okay. I'm inferring that's the best practice.
Yeah, yeah. So the other thing I just wanted to show is there's a neat little demo board that you can get if you're interested in fooling around with this. It's not a lot of money, but they have 18 different things on this little demo board. They have a low-pass filter, a high-pass filter, a band-pass filter, a band stop filter or notch. They have calibrated SWRs of 33 ohms, 75 ohms, 1.5 to 1s. They have some individual components, capacitors, inductors, combination of capacitors, inductors, and capacitors and resistors in different series parallel combinations. They actually have a cal kit built onto this board, a short open load and through. and then they have a 5 dB attenuator and a 10 dB attenuator built onto the board. Now the only problem with this board is okay, so these are the different things that are on the board. I won't go through those in detail, but like I say, there's 18 of them. The biggest problem with this board is this board uses this little funky micro coax plug, which I actually never heard of before. I mean, we've used some crazy, small connectors at work, but I had never heard of this one. But it's a 2 millimeter plug, and you can look I actually found it on Wikipedia. You can look this thing up, but first of all, it's only rated for like a lifetime of 30 connections or something. I mean it's meant to be used, and then you put the cable on and you just don't take it off. Interconnects with inside of some instrument or device. But why they put it on this board? Well, I know why they put it on the board, because it's small, and this is all surface mount stuff. But the board would have been a lot better had they put SMA connectors or something on that board. But if you're interested in playing around with a bunch of different things to measure, different types of filters and components and stuff, it's kind of fun to play with it.
Did you put up the 27? There it is.
I'm sorry?
Yeah, slide 27. Thank you.
Yeah. And then slide 28 is the rest of them. Yep. Okay, well that's it. I hope this presentation provided you with some information on how the Nano VNA works, and how you can maybe use the Nano VNA to do some amateur radio measurements. It's a great little tool. Also, take advantage of that group's I/O site to get support on the Nano VNA. But if you're playing around with this and you get stuck and you have questions, I'm more than glad to help. If I can, send me an email at mycallsign@comcast.net or arl.net. Will get it to me. So thanks for listening, and if there's any other questions, I'll be glad to stay and chat.
Really nice job, Greg.
Thank you.
Very nice job.
Awesome job. Thanks a lot, Greg.